Since for gases, instead of using the mass of the gas, the number of moles is a more convenient measure, we can redefine our specific heats in terms of per mole. So we call that molar specific heat. So basically the heat capacity per mole is called molar specific heat. So if you remember, the definition of heat capacity was the amount of energy you have to provide in order to increase the temperature of a system by 1 degree Celsius. So Q was equal to heat capacity times delta T. And now I define specific heat, molar specific heat, C, that is the heat capacity divided by N, number of moles. So I find that the heat added to the system is now molar specific heat C times N, number of moles, times delta T. However, in gases we have to distinguish between molar specific heat for a constant volume process and for a constant pressure process. So we have two versions of this equation. Q is equal to NCV delta T. This is at constant volume. And then we have Q is equal to NCP delta T. This is at constant pressure. So we distinguish between these two cases. So if you look at the values of Cp and Cv, for a constant volume process at constant volume, if I write the first law of thermodynamics, delta E internal is equal to Q minus integral P dV, or minus integral P dV from V initial to V final. Since the change in volume is 0, the work done is 0. Therefore, the change in the internal energy is given by NCV delta T. If I do a constant pressure process, this time delta E internal will be equal to Q minus P delta V, because it's a constant pressure process. It comes out of the integral. Integral of dV gives me delta V. Then this is going to be delta E internal is equal to NCP delta T minus P delta V. Now, if we are doing the same thing, increasing the internal energy by the same amount by using a constant volume process or by using a constant pressure process, you will find that same two processes yield the same change in the internal energy. Then you will find that NCV delta T plus P delta V must be equal to NCP delta T. So the same internal energy change. So this is telling you that Cp must be greater than Cv. So this is always true. Cp must be greater than Cv. Because in the constant pressure process, Cp accounts for not only the heat, also the work. So it's the change in internal energy plus P delta V. So for a monatomic gas, if I concentrate on a monatomic gas, what's a monatomic gas? For example, helium, argon, etc. There is only one atom in the molecule. The total internal energy of the gas is the total translational kinetic energy, because there is only translational degrees of freedom, and that's equal to 3 over 2 n kBt, or 3 over 2 n RT. Now if I have heat transfer to the system at constant volume for CV, so if I look at this equation at constant volume, I have Q, which is equal to the internal energy change because there's no work. This is equal to NCV delta T. So CV is equal to 1 over N, the derivative of internal energy to temperature, and N times CV is equal to the heat capacity, which is dE internal dt. So using this definition, so let's take this as the definition of CV now. We have, since E internal is equal to 3 over 2 nRT, monatomic case, I have CV is equal to 1 over n ddt of 3 over 2 nRT. So the n's cancel and I get CV is equal to 3 over 2 R, which is 12.5 joules per mole Kelvin. So I have found CV for a monatomic ideal gas. Now, if I look at a constant pressure process that achieves the same thing, so delta E internal is equal to Q plus W, first law of thermodynamics. This must be equal to N Cp delta T minus P delta V for the isobaric process. We achieve the same thing. And since I have PV is equal to nRT, the equation of state for the ideal gas, this is P delta V plus V delta P is equal to nR delta T plus RT delta N, because R is a constant in general. But for the constant pressure process, this part is 0, constant pressure, and also this part will be 0 because N is constant. It's the number of moles. I'm not changing the amount of gas inside the container. So I find that at constant pressure, P delta V for a constant pressure process is equal to nR delta T. So if I look at the change in the internal energy for this process, I will find that this is NCP delta T minus nR delta T. Now, if the same internal energy change is obtained with a constant volume process, this would be equal to NCV delta T. So this is for the isovolumetric process. And therefore I find that N disappears, delta T disappears, and I obtain the following relationship between Cp and Cv. Cp minus Cv, molar specific heat at constant pressure minus molar specific heat at constant volume, is equal to R, the universal gas constant. And this is true for any ideal gas. So I didn't say anything about monatomic or diatomic. For any ideal gas, this relationship is correct. Now, if we go back to the monatomic gas, for a monatomic gas, I have found that Cv must be equal to 3 over 2R, and therefore Cp must be equal to 5 over 2R. Cp minus Cv must be equal to R. And their ratio, Cp over Cv, I define this as gamma, is 5 over 3. So for this monatomic gas, I have Cv is 3 over 2R, Cp is 5 over 2R, gamma, the ratio of Cp to Cv, is 5 over 3. Now there are some important remarks here about this result. First of all, in general, Cp and Cv have contributions from not only translations, rotational and vibrational motions as well. But as we will see, these will be for polyatomic gases. These contributions will come into play in polyatomic gases. And the second important point is that in solids and liquids, you may ask, why didn't we distinguish between Cp and Cv? We only had one C, specific heat. If you look at a constant pressure process where you are increasing the temperature, the change in the volume is so minute because the coefficient of linear expansion is so small, it can be neglected. So a constant pressure process is almost a constant volume process too, because you have very small change in the volume of the system. So since the coefficient of linear expansion alpha is very small, the change in the volume at constant pressure is negligible. And therefore, we reach the conclusion Cp and Cv should be almost the same for solids and liquids. Now let's take a look at the typical values for Cp and Cv. For monatomic gases, you can see helium, argon, neon, krypton. It's very close to 12.5. So you can also see what do I mean by monatomic gases here. These are helium, argon, neon, krypton. And diatomic gases, hydrogen, nitrogen, oxygen, carbon monoxide, chlorine, etc. Cp and Cv values are different. For even more atoms per molecule, I have different Cp and Cv values. And Cp minus Cv is for all gases. You can see here, if you concentrate on this column, Cp minus Cv for all gases is equal to R. We will talk about how to calculate Cp and Cv for polyatomic gases in the next videos. All right, so Let's take a look at an example, a simple example. A cylinder contains 3 moles of helium gas. So N is equal to 3 moles. It's helium monatomic gas. Then you can immediately write CV is equal to 3 over 2R. Cp is equal to 5 over 2R. Gamma is 5 over 3. Total internal energy is 3 over 2 nRT. Only translations contribute to the total internal energy. If the gas is heated at constant volume, how much energy must be transferred by heat to the gas to increase its temperature from 300 Kelvin to 500 Kelvin? So Q is equal to NCV delta T, and it's going to be 3 moles, 3 over 2R, 8.312 joules per mole Kelvin, that's R, times the temperature difference, 500 minus 300 Kelvin. So this is going to be 7,500 joules. And now if I do this at constant pressure, how much energy needs to be provided? So Q is equal to NCP delta T now. It is 3 times 5 over 2R, 8.312, times 200 Kelvin, the temperature difference. It's 12,500 joules. So you can see that in order to do this at constant pressure, I have to provide more heat into the system.